This is the first of two videos. It's going to introduce us to Bayes' theorem. I'm going to go over Bayes' theorem in more detail next week, but I want to get started this week to balance the workload. And I want to begin with a review of a couple things. And the first thing is, what is the meaning of this expression P of y? And the point I want to make is that it can mean three different things. One is that it could be a function. So a function acts like a meat grinder. So here I'm taking this single value of y, putting it into my meat grinder, which consists of this function. And what comes out the other end is the random variable that, the probability I should say, that the random variable uppercase y will take on a value of lowercase y when the experiment is actually conducted. A second meaning of P of y is it can refer to a single value that's produced by this function. So for example, if I put a value of 3 for y, what might come out the other end is a value of 0.6, which is the probability of getting a value of 3. Alternatively, it can refer to an entire probability distribution. So I could put in all possible values that I might observe for y, and what would come out the other end would be the probability of each of those, and the sum of each of those would be equal to 1.0. So these are three possible meanings of P of y. Second thing I want to go over is the binomial distribution. The binomial distribution is really important because weeks 1 to 6 of this seminar are going to be based on the binomial distribution. And the binomial distribution comes into play when we've got a binary dependent variable. And what we mean by binary dependent variable is that it's a variable that can only take on one of two outcomes. So for example, a red marble versus a white marble, a female versus a not female, true versus false, alive versus dead. And if we have a binomial distribution, what we're inherently assuming is that the results of an experiment to which the binomial distribution is relevant, the results are dependent on an underlying process. And this whole idea that the results depend on some defined underlying process is our key feature of Bayesian data analysis. So then to come back to the idea of what is the process we refer to as a binomial process, well, first of all, there's only two possible outcomes, success or failure. The choice between them is somewhat arbitrary. The random variable that we're dealing with is uppercase y, which is the number of successes. And in any experiment, we observe y, lowercase y, observed successes when we actually do the experiment. These y observed successes occur in n independent trials, and the concept of independence is very important. And as we go through these n independent trials, the value of theta, the probability of success in any one trial, remains constant. And so if all those features exist, then the appropriate formula for the binomial distribution is given here. So that's just a bit of review. Now what I want to do is get us started on Bayes' theorem. And I'm going to try to illustrate that by way of an example that is provided by Kruschke. And he says that there's this coin company, Acme Coin Company, that makes two different types of coin. And the first type of coin is head biased. And if it's a head biased coin, then the probability of it coming up heads in any one flip is 0.75. If it's a tail biased coin, then the probability of it coming up heads in any one flip is 0.25. So I've got this coin in my pocket, and I'm wondering whether I've got a head biased coin or a tail biased coin. And what I'm going to set out to do is calculate the probability that in fact I have a head biased coin with theta is equal to 0.75. But I have some prior information because I have an informant who works at this company who thinks that the coin that I have came from a batch that was head biased. And I rather trust my informant. So prior to any information, I think there's about an 80% chance that the coin that I have in my pocket is head biased, which is equivalent to saying that the coin in my pocket has a value of theta is equal to 0.75. So then I do a little experiment where I flip the coin 10 times, and I observe 4 heads in those 10 flips. And that's a little bit of a surprise to me, because, if my informant was correct, and I actually had a head bias coin with theta is equal to 0.75, I'd expect to get more than 4 heads in 10 flips. So I'm somehow going to have to reconcile my prior belief with the data that I obtained. And that reconciliation is going to be obtained by running the prior and the data through Bayes' theorem, and that's going to enable me to calculate the posterior belief that I have a head bias coin with theta is equal to 0.75. So now I want to think about derivation of Bayes' theorem. And what we can say is, what we saw earlier, is that the joint probability of a tree being of a species and in a particular height class could be obtained by the conditional probability that it was of a species given that it was in a height class multiplied by the marginal probability that it was in that height class. But alternatively, we could calculate that same joint probability by taking the conditional probability that it was in a height class given that it was of a species multiplied by the marginal probability that it was of that species. And so we can just rearrange this and say that the conditional probability of being of a species given the height class is equal to the conditional probability of being in a height class given that it's of a species multiplied by the marginal probability that it's of that species divided by marginal probability that is in that height class. And so now all I'm going to do is I'm just going to make a very simple substitution. So instead of S, I'm going to say theta, and instead of H, I'm going to say data. And if I do that, what I get is probability of theta given data is equal to the probability of data given theta times probability of theta divided by the probability of data. So these two things have exactly the same form. But now I'm going to use this thing to solve my problem. And to do that, I'm going to provide a little bit more detail. So instead of this, what I'm going to have here is this. So this is my target. Really, what I'm interested in knowing is what is the probability that theta is equal to 0.75. In other words, what is the probability that I have a head bias coin conditional upon the data? Conditional upon the data, which was that y was equal to 4 and n was equal to 10. So I've got these different components. And this is a really important one here. And I put this thing in square brackets, although I really didn't need to do it. So this is the probability that theta is equal to 0.75. This is the probability that I have a head bias coin. But more importantly, in the context of Bayes' theorem, this is my prior. This is my prior probability that theta is equal to 0.75. That's based on my informant. So the prior probability is going to be 0.80. So the whole idea of Bayes' theorem is that we're going to start off with some sort of prior belief. Then what we're going to do is we're going to collect some data. And these two components are going to capture the data. And then ultimately, we're going to come up with our goal, which is the posterior belief that we have a head bias coin conditional upon the data. So we're going to stop here and we'll pick it up in the next video.